So, are we all ready to hear the funny guy at Multicore World? Because I mean, no, he's the man. And some of you who haven't been at previous editions of Multicore World, you missed probably my dear friend Ruud speaking about open wounds. But the ones that remember, they will remember open wounds. And by popular demand, we won't ask you to repeat that so far. So, yes, go ahead, please.
Thank you, Nicholas. I wasn't expecting to see myself here. Can we switch the view? Oh, that's better. I'd rather have that. Yeah, open wound was a special thing. I'm not going to talk about open wound. And thank you for putting up with me, for getting me back here. It's good to see many familiar faces. And I'm going to talk about something that's a little bit different than what I usually talk about. It's about a tool called DTrace. And I first want to start with two questions. Those are the questions that actually drove me to suggest to Nicholas that this could be a topic for Multicore World. And I know he likes controversial things. He likes to have discussions, so we'll see. And the tool is called DTrace. So I'm going to explain a bit what DTrace is. Then I'll talk about concepts in DTrace to the bare minimum, because I want to get to the second but last bullet, scratching the DTrace surface. In other words, an example where I want to show you the kind of things you can do with DTrace. I'm calling it scratching the surface because it can do so much more. And by the way, for those of you that think I got very rich by selling DTrace, yes, I do. I get 10% of a free license. So I'm making lots of money here. Then at the end, we have a Q&A. I always find it fun. In Q&A, suggests there's a one-to-one mapping between a question and an answer. No, I'm not suggesting that. You can ask a question, and I'll try to give an answer in the best effort. All right. Two questions, and it just struck me that we all know about that. I don't have to really remind you of things like CrowdStrike, or before you show up at the airport, the airline sends you a message. Sorry, our check-in system is down. Be prepared for serious delays. So we know about all these huge, massive outages in systems with a big impact on convenience, on money and time. And my question, that's an open question. On Wednesday, we'll have a panel session about it. Is anything done about it? What are we doing as a society? What are we doing as scientists to make things better? With a lot of focus on security, which is a good thing, but how about robustness? And that led me to, well, maybe I should talk about a tool called DTrace, and that's what I'm going to do next. And actually, when I prepared this talk, I thought, what did I get myself into? Because I think this is going to be the most technical talk I've given at this place. So we'll see. First of all, when you look at the current tools available for troubleshooting, there's a long list here, and there are many, many more. But one thing that struck me is they all sort of have a very limited focus. For example, you can look at I/O. You can look at what your network is doing. But no tool will tell you what your I/O is doing while your network is busy. And maybe that was the cause of the problem. So you don't have that correlation. You don't have that holistic view with those tools. In themselves, they're perfectly fine if you have a fairly simple problem to troubleshoot. But if it gets more complicated, I don't think they'll be very helpful. Another thing is you can't customize it to your need. You get tons of options, but if you don't find what you're looking for there, you're sort of stuck. And that brings me to DTrace, because DTrace is very different. And this is all, DTrace is very old. The first release was in 2004. It came out, Sun Microsystems developed it, and it was part of the Solaris operating system. And this was the question that drove the development of DTrace. And the interesting thing is to notice nothing has changed. You have a complex system, something unexpected has happened, and you want to know what was happening and why, but you can't do what you would like to, like take the system down or do something else very disruptive for the operations. What do? And that actually led to the development of DTrace. When you read the first paper written by the authors of DTrace, that's what they start with. I'm a simple person. My simple description is, what is DTrace? Well, DTrace is your microscope into the operating system. It really tells you what's going on. And that's actually what you need in the more difficult cases, because you can see what the OS is doing, what sort of decisions it may make, and whether you like that or not. So what is DTrace? DTrace is a dynamic tracing tool. That's what it stands for. Actually, it's not really a tool. I think one of the things that we collectively did wrong is position DTrace as a tool. It's more a programming language than anything else. DTrace is not a fixed command, and that will help you do the troubleshooting. You write your own tool in that programming language. And I'll get back to that, and you'll see lots of examples. One of the nice things about DTrace is that you can do your tracing in both in userland and the kernel and both. So you may start with your application in userland, then you go down and you need some operating system service, and that's where like, for example, profiling tools will stop, and you get the result. DTrace will allow you to go down into that kernel and see what's happening there. And I think that's one of the very strong points. So it does provide that holistic view. And from day one, it was designed to be safe on a production system, so you can use it on a running system. So how does it work? You write your program or script in a language called D, and I can see some of you silently sort of cry, like, no, not another language. No, D has stolen everything from C, C++, awk, and all those shell programming that we have. So if you've done any of that, you'll find the D language to be very, very familiar. Nothing really new. But with that, with the programmability, you get full control over what you want to see and how you want to expose that to the outside world. And one of the things is very natural in DTrace is to look at different aspects of the system. So you can see whether there's a link, maybe some buffer is overflowing because something else that's happening. And that's what you can do with DTrace. Also, the way you want to report your results, that's up to you. You write it. So you can completely customize it. You typically don't need any post-processing tool to massage the output that comes out of it. So it gives you flexibility and customization. Some concepts that I have to go through is the probe. It's all about the probe. A probe is an event that you can monitor, nothing more or less. And with every system where DTrace is installed, you get a fixed set of probes, and that's what you're going to work with. But don't worry, you typically get like 100,000 probes to choose from. And there's a command to list them, so you can see that. And they're grouped, but essentially you have a lot of probes to do. Even if you want to write your own probes in your application, you can do it. So you can use, other people can use DTrace to analyze what's going on. So you get a lot of flexibility there. An example of a probe is, let's say you want to monitor a kernel function. You can write a probe that will tell you now you're entering that function. You can ask for all sorts of information, and you can do the same on the return. That's just an example. And what you're going to do, you're going to write a probe, and you're going to define the actions that you want to take when that probe executes, or the DTrace terminology is it fires. The probe fires, and you tell it what to do. Yeah. And here's the general structure of a probe. The definition has 4 fields, maximum 4 fields. The provider, so each system has providers. For example, there's an I/O provider, there's a networking provider, and that will give you certain probes to choose from. The module is where things live, could be in a library, for example, or an executable. Then the function that you want to probe, and the name, for example, entry when you enter the function. And then you have the statements, and again, that's what you type in. There's one thing that I added here, that's an optional predicate. That's like an if statement. So the probe doesn't have to be enabled if you don't want it. You can write your conditions and saying, well, I only want you to fire if this sort of thing happens. And that turns out to be a very flexible and powerful concept to restrict the tracing and get more manageable output. Time for an example. Here's a very simple example, but it works. I'm using the system call provider, the syscall provider. That's the first field here. And then I want to restrict my monitoring to the VM Linux module. Again, that could be a library, it could be an executable, it could be anything. And within that, I want to look at the bind function. And I want you to fire or execute when I enter that function. And here I have a very simple printf function. Anybody familiar with C, C++ will know that function, printf. And what I'm doing, I'm using a built-in variable probe func that will give me the name of the function. So as simple as this is, this will already tell me on my system whenever the function bind is being called. And that's all you need to do. In general, your probes will be a little bit more complicated because you want to know more. So one thing I can do here is I can leave out the field for the module here. So I don't care where it comes from, whether it's VM Linux or somebody else provides it, I don't care. And that allows you to cast a wider net because initially you probably don't know exactly what you're looking for. You're looking for a needle in a haystack. Here, same with the bind. I use a wildcard bind star, means I want to see every function that starts with bind because I don't know. I don't know which one is actually the one that I'm interested in, who's being called. Then I have that predicate, my flag equals 1. So this will only happen under conditions that I set. And once all those conditions are met, I get my print statement. And what I'm going to use in the example that I want to get to as quickly as possible is the PID provider. The PID provider, process ID provider, will allow you to specify a target, and that's the process ID of what you want to monitor. And $target is a symbolic variable that expands to the process ID. You say, I want to monitor this application, and you figure out what that means. Right? Very useful, and in that way you can, again, restrict your tracing. If you don't do that, you can do the system-wide tracing. You can look at everything happening on your system. Generally, that will not be very meaningful, but you can. So I'm going to use that PID provider, and within my probes, I'm going to use a data structure that's called an aggregation. And that's a really powerful concept. For those of you familiar with those concepts, it's like an associative array. And what it is, it mathematically, an aggregation stores the result of an aggregation operation. And what it means is you got lots of data and you reduce it to less data, not necessarily a single number, but for example, the minimum of a set of numbers is an aggregation function, likewise the maximum. And with that, you can have a very flexible index as you would have in an associative array, as opposed to a regular array which will only have an integer as an index. And here's my example, and of course we all like to kick Nicholas as much as we can. And here's one. Let's say I'm still trying to convince Nicholas to use DTrace for his administration of multi-core world. That's a bit of an ambitious goal, but let's say I want to have that. This is what he could do. First of all, you start with the @ symbol that defines the data structure to be an aggregation, and the reason it's an aggregation is because I'm using the count function on the right-hand side, and that's one of those aggregation functions. It increments by 1 each time a probe will fire. And that's a great way to get like function call counts. You put it in your probe, and each time you hit the probe, it will be incremented, and you know how often the function has been called. As the key, again, it's like an associative array. I'm using two fields in my key, the year, an integer, and a string like the year and the location. So that's called an aggregation. And again, anybody that's been using associative arrays will sort of recognize this. All right, in my aggregation function. Now, before I continue, and I'm afraid I may lose some of you, in case you're still interested at the end of this talk, there's some videos on YouTube that can get you started. They're training videos. They're free of charge. I made them in my Oracle days, and hopefully it'll get you started. And otherwise, just send me an email. I'll be happy to talk about DTrace. My example, I call it scratching the surface because there's so much that I'm not going to talk about. But here's what sort of triggered the example. Monday morning, 9 a.m., and you get that email. And it's talking about the company wants to launch an important application called Black Box. And there's going to be a meeting in an hour from now. And in that hour, that's going to be the go, no-go meeting for the launch of that application. And the question is, can you give me I/O characteristics of the application? And by the way, this comes from the VP A. Hall, who is in charge of advanced generic technology. And what he wants to know the file names that are used by that application, the descriptors, and how many bytes are being read and written. And you got 1 hour to come up with that. How would you go about it? Well, for the impatient ones and those of you that like to go back to email, this is the result. I'll show this again 10 slides from now, but this is what I get out of the system with DTrace. And when we get to that, you've seen all the bits and pieces here, and since I don't have a lot of time, I'll be brief on it here. You can see which functions are being used. You can see the file names here, and this part is the I/O reading and writing, how many bytes I'm reading and writing. And you can just get that out of the application without doing anything other than writing your DTrace code. You don't have to do anything with your application. So let's get started. You run the application, black box, it takes an input file, and that's it. It doesn't produce any output, could be like a daemon for that matter. You have no idea what's going on, so let's get started and find out. The way you use DTrace is you cast a wide net, because by definition, you don't know what you're looking for, otherwise you wouldn't have to look for it. So what you do, you use those wildcards that I was talking about to say, well, just show me what's going on, and then hopefully that will give me inspiration where to zoom in. That's the idea. And then for each piece of interest that you find, you write your probes and you collect whatever information you want to gather, and that's exactly what we're going to do. And very often you can break it down in sub-problems. Like in my case, I can figure out the file names and the file descriptors. That has nothing to do with how many bytes I'm reading or writing. And that will make the whole development a little easier. And then in the end, you literally glue it all together and you have your total script or program to give you all the functionality. So let's start. And I'll start slow, I'll speed up a bit because there's more of the same at some point, but I just want to show you the whole process. Here's my very first probe. I have 6 lines of code here, and the first 3 define my probes. And note that I'm using this bit $target. Then you see colon, colon, that means I don't care about the module. I don't care where they come from, because what I do want to know, I want to know the read, write, and open functions. But inside the system, they're often called differently, I don't know, so I just use these stars. Just show me everything with the names in that. Of course, you'll get much more output than you probably care about, but that will certainly contain what you're looking for, because those are the functions that open the file, they do the reading and the writing. That's what I know. So that's step 1. Then I have a single line here. I have my aggregation, I call it target calls, and my key has 2 fields, the function name and the module. So that will show me all the functions that meet these criteria, and I do the count, and I know exactly how often they're called. That wasn't asked for, but it's a freebie that I get this way. So that's what I'm doing here. These 6 lines is literally all that you need to run your program. You need to run it under control of DTrace. And given by the nature of what you're doing, you need to have the right privileges, so you run it under sudo or as root. And you give it a target at the end, at the right hand over there, that's my black box application, and I tell DTrace, this is the one that I want you to trace. And this is what it shows. And one thing we see here, the yellow line, is from DTrace. That's one of the default outputs. It tells me that altogether I had 391, almost 400 probes that actually were enabled as part of my wildcard approach. Way too many, so I got the whole list here. You can see how often they were called. So I got a lot of output, but what I see here, I see 3 functions of interest. A function called open, a read function, and a write function called pwrite. Apparently that's what this application is doing. It's doing some more, but for this purpose, I'm going to focus on these 3 functions because they look like interesting. Typically, your next step is to find out what are those functions actually doing, so you can check the man page or some other documentation. And what I find here is the open call. The open call takes the path name. That's my file name. So that's the one that I need to capture. And it returns the file descriptor. So those are the 2 values. Once I have those, I know the files in use and the file descriptor they connect to. In the read part, I read from a file descriptor, and the last argument is how many bytes you're reading, and the return value is how many bytes you've actually been reading, because that doesn't have to be the same. Same for the write, for the pwrite, you read from a file descriptor a number of bytes, and it'll tell tell you how many bytes you've actually been writing. So that's what I'm going to work with now. And before I'm showing you my code examples, all codes start with the first 6 lines, start with this. Line 1 here avoids that I need to type in DTrace on the command line, and it's like a step to hide the use of DTrace to others. So that's just a little convenience. Then I have at line 3, I don't want to see the DTrace default output, and I have two settings to control the way my aggregations are printed. That's not in your first DTrace program you'll write, but at some point you want to start customizing things. And this is, I just wanted to be honest and show it, because this one, they all start at line 7, not at line 1, and that's why. They're straight from the code. So what we see here from lines 7 to 12 looks very much like what I was showing before, but now I dropped all those wildcards because now I know exactly what I'm looking at. Open, read, and p-write. And whenever I enter those functions, I have my same aggregation here, but now again, I start to focus on these 3 functions. The new sort of element here is the one from 13 to 16, where I have a specific probe for the open call. And now it starts to get interesting, because when I get into the open function, recall that the first argument is the name of the file. Well, that's stored in a variable called arg0. That's what you find in the manual. The first argument is in arg0. So when I capture that, I have the file name, and all that I need to do is get the file descriptor. Well, that's a little bit different, which I'll show next, but this will give me the file name and how often I call it. So with that, I have done printing my results, and I'm not going to spend a lot of time on that. I use printf to print some file headers, and then the print a to print an aggregation, which is very similar like printf. And this is just the output part. It's about half of the code, but it's not very exciting, so I'll be very brief on it. I run my program as you saw before. I run it as sudo, and now I get this output from what I was just showing. What was that, 5? No. So I have my open, p-write, p-read. I know where they come from. And here at the bottom are these 3 files. So I have that information already in my hand now. I know this program is using 3 different files. And I know how often it's reading from files and how often it's writing. But I want to know more, because I needed to get the file descriptors. And that's what I'm going to do here. I have a new approach now, because what I'm going to do in the entry to the open, I can get the file name. I've just shown you that. But instead of printing it or storing it, I'm storing it in a variable. And that variable will carry over to the return part. So I'm in the function, I capture the file name. When I'm leaving, I know the file descriptor, because you don't know the file descriptor until you're at the end of the function. And with that, that's stored in arg1, and here these 2 blue things couple the file name and the file descriptor. So I have that part of the information. Again, I realize this is going very quickly. It's not, don't expect everybody to understand all the details, but that's how you sort of approach it. And there we go, output. I run my program as usual, and now we're there. We have the function name, open, we have the 3 file names, and we have the file descriptors. So now I know that, and that was one of the pieces of information I had to provide. I was also asked how many bytes are we reading and writing, and this starts to be a little bit more of the same. I have 2 probes on the read function at lines 7 and 12, and again, I'm probing the entry and the return. In the entry, I set up 2 aggregations, and this is why I wanted to show you this way. I use the function name, which is read, and this one uses arg0, and in the read, that's the file descriptor. So I'm differentiating across file descriptors here. And what I'm doing, I'm summing up the number of bytes that have been requested to be read. The second line doesn't have that arg0, because I also want to get the global total, all the bytes that I've been reading. So with that, I can get the differentiation according to the file descriptor, and I can get the grand total. I don't need to write any post-processing tools to get that for me. Then the second part, in the return part, I know how many bytes have actually been read, because these two numbers need not be the same, how much you want to read and how much you get. So that's stored in arg1, and I just sum it up. So that's what I'm doing here. I get my file descriptor, I have the number of bytes that I'm going to read, and I know how many of actually I have been reading. Print statement, run again, and now I have these two tables, and there was only one file descriptor here, number 3, and that's the number of bytes that have been read. And the interesting thing is, when you look at what's actually been read, it's less than what you asked the system to do. And that was simply because the file wasn't as large as you requested. That's a very natural thing. You're reading on a 4K page size basis, but here you see exactly what you're trying to read and how much you got. The write, and then we're done. The write is very similar. What I have on the entry here, I have my file descriptor, the number of bytes that I'm trying to read, and that's it. I have my output, I run as usual, and now, since I differentiate on the file descriptor, I see that I've been writing to 2 different file descriptors and only 4 bytes each, and the total is 8. So I let DTrace do that simple computation for me. And that was a very, very quick overview to show you how you get this kind of output. And luckily, I finished 5 minutes before the end, so there's time for a coffee, and for you, there's time for the questions.